Welcome to Digital Switching System 17EC 654 virtual class. Today we will discuss a mathematical model of telecommunication traffic. Why do we require a mathematical model? In order to obtain analytical solutions to a teletraffic problems, it is necessary to have a mathematical model of the traffic offered to telecommunication systems. A simple model is based on the following assumptions: a pure chance traffic and statistical equilibrium. Next, we will see these two models. The assumption of pure chance traffic means that call arrivals and call terminations are independent random events. From the name pure chance, it means that it is independent random events. Calls made by an individual user, of course, are not made at random. You know that. However, the total traffic generated by a large number of users is observed to behave as if calls were generated at random. If call arrivals are independent random events, their occurrence is not affected by the previous calls because it is a random event. The traffic is therefore sometimes called as memoryless traffic. The assumption of random call arrivals and terminations lead to following results. First, the number of call arrivals in a given time has a Poisson distribution. Therefore, probability of number of call arrivals in time t is given by mu to the power of x divided by x factorial into exponential negative exponential of mu, where x is the number of call arrivals in time t and mu is the mean number of call arrivals in time t. And for this reason, pure chance traffic is also called Poissonian traffic. Second result is the intervals t between call arrivals are the intervals between independent random events. These intervals have a negative exponential distribution, where probability of capital T greater than or equal to t is equal to e to the power of minus t by t dash, where t dash is the mean interval between call arrivals. Next result is, since the arrival of each call and its termination are independent random events, call durations t are also the intervals between two random events and have a negative exponential distribution. Probability of uppercase T greater than or equal to T is equal to e to the power of minus T by h, where h is the mean call duration or holding time. Now that we have seen three results and three equations, it is time to solve some problems. Before solving problem, let's recall the results. The probability of call arrivals at a given time t follows Poisson distribution, whereas the interval t between call arrivals, that means between two calls, the interval follows exponential distribution. Similarly, the call duration also follows exponential distribution. Now let's solve some problems. First problem. On an average, one call arrives every 5 seconds. During a period of 10 seconds, what is the probability that no call arrives, one call arrives, two call arrives, more than two call arrives? This is what you have to find. So what is the formula? Probability of number of call arrivals p of x is equal to mu to the power of x divided by x factorial e to the power of minus mu. Therefore, first we need to find mu. Mu is equal to, since from the data it is given that one call arrives every 5 seconds, therefore it is 1 by 5 into total period, which is 10 seconds. So 1 by 5 into 10 is equal to 2. Therefore mu is equal to 2. Now let's solve for the first, no call arrivals. No call arrivals means x will be equal to 0. So if you substitute x is equal to 0 and mu is equal to 2 in the equation, we get the first result. Therefore, p of 0 is equal to 2 to the power of 0 divided by 0 factorial into e to the power of minus 2. 0 factorial is equal to 1. Therefore, 2 to the power of 0 is also 1. Therefore, it is equal to e to the power of minus 2, which is equal to 0.135. Next, we'll solve for one call arrival. Now, x will be equal to 1 and mu is equal to 2 only. Therefore, p of 1 will be equal to 2 by 1 factorial into e to the power of minus 2, which is equal to 0.270. Similarly, for 2 call arrival, P of 2 will be equal to 2 square divided by 2 factorial e to the power of minus 2, which leads to 0.270. Now, more than 2 call arrivals, that means P of x, where x is greater than 2, will be equal to 1 minus P of 0 minus P of 1 minus P of 2. This is because the total probability will be equal to 1, and we have already calculated for P of 0, P of 1 and P of 2, and we want now more than 2 calls. Therefore, P of P greater than x greater than 2 will be equal to 1 minus P of 0 minus P of 1 minus P of 2. Now if we substitute all of that in this equation, 1 minus 0.135 minus 0.270 minus 0.270, we get 0.325 as the answer. This is how we have to solve. Let's solve the second problem. In a telephone system, the average call duration is 2 minutes. A call has already lasted 4 minutes. What is the probability that the first one, the call will last at least another 4 minutes? The call will end within the next 4 minutes? Let's see the solution. Since the average call duration is 2 minutes, h will be equal to 2. And we need to find the call will last at least another 4 minutes. Therefore, small t will be equal to 4. Therefore, probability of capital T greater than or equal to small t, that is greater than or equal to 4, will be equal to e to the power of minus t by h, because this follows exponential distribution. So substituting for t is equal to 4 and h is equal to 2, we get e to the power of minus 2, which is equal to 0.135. Now the second one is the call will end within the next 4 minutes. So if you see the second problem, it is the negation of the first problem. Therefore, probability of t is less than or equal to t, which will be equal to 1 minus probability of t greater than or equal to t. Therefore, we have to solve 1 minus 0.135, which is equal to 0.865. Till now, we have discussed the first assumption, that is pure chance traffic, and we also solved some problems. Now let's discuss the second assumption, that is statistical equilibrium. The assumption of statistical equilibrium means that the generation of traffic is a stationary random process. That is, probabilities do not change during the period being considered. Consequently, the mean number of calls in progress remains constant. As per the syllabus, you don't have any problems on statistical equilibrium. Therefore, we'll stop now. Thank you for watching.